Alrighty, hi guys. Just a bit of an update on this Math64 compiler, runtime, whatever you want to call it. If I look at here's the example code. Very simple. Some variable declarations and one expression. That's all it can do. Isn't that exciting? Not really. Let's run it. I've stretched the windows out, etc., so we can see what's happening on screen, and changed the debugger font. On our left-hand side, we see a version of the input code. That's this code here. So we're proving that we've lexed it appropriately. We've decoded these things as in this case, word tokens, and then they've been reclassified as keywords. So in this script, we'll actually have var for variable, and then a list of these tokens behind it. I wanted to make sure it's working, so I've got two of these declarations here. We can see it's working down here. We see that these are the variable names. Just here, we've got A, B, C, D, and a variable called result. And a bit of information about what we're storing about the variable. I guess a quick overview of how this variable table works is in the compiler anyway. It stores a classification of what this thing is, its displacement on the stack, a bit of a quick hash to make sure. So if we have long variable names, we can use an integer for comparison purposes. When we're searching for variable names, we've got an offset into our global string buffer for all of the variable names and the length of that fragment in text. That's all we need to store. Pretty simple. Up until today, actually, it didn't do anything. It was I'd written all the code and it compiled, but it was sort of working, but not actually working, if you know what I mean. It turned out that some of one of the variable table routines was broken. It was looking at the wrong thing, and the bytecode producing part of the program was actually dodgy as well. One part of the code I was assuming I was using an offset to this base chunk of memory, and then in the other part of the code I was assuming it was a pointer pretty much. And since it was probably a week between when I wrote the first bit and the second bit, I just assumed that was the way it was, and then so I'm running it and it's crashing all the time. I think that's kind of weird. What the hell's going on? And as I went back through it, I went, oh, okay. Once I did that, it pretty much came to life. So let's go through this information on screen. So this is our variable table. We can see we've got more variables created than we actually declared. And I'll get to that in a second. Our expression up here, the compiler at the moment is running through our program after it's lexed. It understands the var keyword. It keeps stepping down until it finds a variable and then an assignment after that. Standard sort of basic syntax. It just assumes that what's on the right hand side is an expression. So it passes this to the solver. Here it's just doing additions and subtractions, but we've got an addition with a literal plus, we've got A plus 100 plus B plus C minus D. So it sweeps through the expression and solves these things down to here. This is the actual bytecode to be produced. It's a text representation of what's happening. You've got to understand that on the back end, the bytecode has nothing special about it. All it is it's doing these operations against offsets in the variable table. So this first addition here, I've got add 48. So I've got an addition that occurs between the variable at offset 0 and the variable that appears at offset 40. If we look these up, these are stack offsets, by the way. That stack offset 40 is a literal, and that would be the literal value 100, as we can see up here, because the right hand term. The left hand term is stack offset 0, which is going to be the variable a. So we're going a plus 100, and we're storing the result in our temp. Pretty basic way of doing it, but it means that we don't need to have anything different in the runtime. The runtime just has one concept: variables. Everything's a variable. It means we don't need versions of instructions that do things like, I can just have one addition instruction, one subtraction, etc. Otherwise I would need to have things like a version of add that has literal support, so I can have result equals variable plus literal. Then there would be a version, well, it doesn't need to be, but there would be other variations of the same thing. Sometimes you need to have other definitions of them or other versions of those instructions because you need the order matters. So if I'm doing a subtraction, for example, if I have result equals result equals a minus c or a minus b, then it matters that we're subtracting b from a. I can't just flip the terms around. Right, so we've got our add opcode here is working. We're doing another add. We're adding the result of this to the result of b. We're adding the result of all of these terms with this to c. And then we're doing a subtraction at the very end. And that seems to work. Now I have got nothing in this example that tests the runtime code. At this point, I'm just making sure that I can view what's in the expression buffer, I can view the variable table, and the thing at the bottom here is the expression buffer. So when the compiler is scanning through, and it sees this case here of variable equals something, it knows that this is an expression. It sends these tokens off to the expression solver, and it just churns away until it gets it either finds something it doesn't understand, which at this point is most things it doesn't understand, because all it can do is add and subtract. So it just keeps churning away until the result is one result that's left over. If there's not, and it gets stuck, something is broken that it doesn't understand, or if it finds something that it obviously that can't understand, like if you have a malformed expression, like if you have a function without some brackets or something like that, where it's not expecting to see that particular command in that usage or something. So it gets passed off to the solver and gets churned through the expression buffer, and down here we're looking at the contents of the first 8 tokens in that buffer. At the end of this, the result should be in the top token. Should be, if it solves correctly. Which in this case I know that it has actually. There's a variable up in the structure up in here that tells me this is okay. I've used error status as a way of reporting if everything went okay and nothing died, then hey, set this error status offset or this field to this value. So I know it passed all the way through, did what it's meant to do, and then I told it to exit because I wanted to make sure that it was working to this point and not crashing somewhere else. Wow. Make any sense? It's a lot of hassle for doing a little math solving thing, isn't it? But once we get code stable, it's not making dumb mistakes, which is what you kind of expect this sort of thing to do, given that it's literally thrown together. within a few sessions, pretty much. If we go and have a look at the project, so this is the test project in PB. So I'm using PB for display purposes, pretty much. I've got the library in the back here. I've just written some functions that decode the structures that I'm passing back. And we've got the actual work is just done with the C. The library's written in C, which is just Visual C 6. I like the older version of Visual C, and it doesn't like running at Windows 10. I've noticed recently. This is the decoding code. So as I was talking about the other day, we've got structures that represent the opcodes. These are just patterns in memory. This is a math instruction there. We've got our instruction, our destination variable. I've called it in this case. It's really a stack offset. The left stack offset and the right stack offset. So if you have a look at what this loop that does the execution, which is not hooked up at the moment. We've got a move instruction over here that can do a literal move into a variable, which we haven't got anything on the compiler side to generate this at the moment. We've got an instruction that'll zero a variable. I'll have another one that does sets a variable to 1. Same as like pi and those kind of things, where those literals built in. So our addition is we grab the current instruction address and recast it to our math opcode structure. We have our destination variable equals our source left-hand term plus right-hand term. That's an addition. Surprise, surprise. So the compiler will actually solve all that stuff out for us. The C compiler will actually solve all that stuff out for us. If you look in release build in here and just have a quick look at what these things actually generate, if you're curious. This output here is a combination of the C code mixed with the assembly that's been, actually the binary's been produced. So I can compare what's produced with different patterns of code. For example, here's the machine code that does the, in PB terms we would know this as a select statement. So we're doing, our variable here is ECI, we're comparing if it's greater than ECI and branching past this if it's outside of our legal options for our select. Clearing this thing, grabbing an offset and then jumping to it. This is a table down further. And this is automatically scaled. Our move instruction becomes this. We grab a couple of offsets in EDX and ESI. We move our bytecode pointer forward and then we do the move operation here. Now, since PB is 32-bit, we don't really, and I'm using Visual C6, which is 32-bit compiler. It's going to generate 32-bit code for doing those operations. So a move is just moving the two integers side by side, or longs side by side. Does the operation here, jumps out, continues the loop, etc. So our addition, which I've got marked up here in the there's a bit of marquee code. Same thing, grab the offsets here, moving the bytecode pointer forward, and with because the FPU has a 32-bit mode, a 64-bit mode, you can read either of the two. So you can read a 64-bit float or a 32-bit float. Here we're doing a read, whatever this address is going to be, putting it onto the FPU, which is a different part of the chip, they're different registers. We do our addition, and then we store the result out. That's it. So our 64-bit addition turns into pretty much 6 instructions. Not too bad. Now, if you wrote it by hand, you could get this to be better, but for an interpreter, it's going to be pretty good. The key point here is that this little runtime, this little interpreter will be so focused on doing one thing and one thing only. So it only does float operations. That's machine code. Isn't that exciting? Back to the C code. Here's the rest of the decoding code. So we've just got 4 operations being supported. We'll have some, math functions that I'll drop in afterwards. I couldn't be bothered. So as I was talking about the other day, this does it uses structures to write the bytecode, and I've defined the structures up at the top, which is just like a type, pretty much a types structure. We can have these things. So that this pattern of these variable offsets here is how I'm writing the thing into memory, how I'm decoding it at runtime. I just thought I'd try that. I've always wanted to try it. There's a bit of code for defining the instruction set. If you head across to our view, we can look at things like the compiler parse. It's just straight C pretty much. I've got a string pointer coming in. We're lexing this out. We're checking if there's anything, if there's any known tokens in it. Not because the file might be empty. We're making a program. And we start decoding. Because it's lexed out for us, we run through the list of tokens that the program was broken down into. We don't have to worry ourselves about white space or trying to classify what these things are. We just go, give me the current token. It's the keyword variable, so it's a declaration statement. Call the code that does the decoding of that statement in particular. And we just continue on looping. I've got a word here as well. This is when an unknown token equals an expression. So we find the variable in the program. We go, okay, we found something. You must exist. Otherwise, we throw an error. There's nothing to throw errors at the moment, so I just put some dodgy data in those things there. We grab the next token, see if you're an equals. If you're an equals, okay, cool. Solve the expression. And we either get an expression that solves down to one resolve, or we get something that's broken. Before I was talking about, I put 999 in the expression to show us that something went okay. So here we would get, if the expression is not one token long, if it misunderstood something, like if you put 2 variables side by side, it would break the expression. We'll try that now actually. So we would get 555 as a resolve. Back to the test program. Where are we? So let's put, if I put space and then D again, then we should actually get something that doesn't solve. We've got our instructions, that's all good. But if we go check the status of what the program, we find error status 555. So, and the last expression was 2 tokens long. It doesn't know what to do with it. It sees the 2 word tokens sitting beside each other, the 2 D variables, and goes, well, what am I meant to do with that? Because there's no way of reporting an error, so, and it won't have verbose error detection. It'll just have some crappy error codes, and you'll have to print them out yourself. Hey, it's free. Who cares, man? Back to C, I guess. So our solve expression, which is what we, before when we had something that wasn't, that was longer than one token long, we just put quad 5 in our error status and abort it. So even though it's a pretty simple program, it's got a bit more code in it than what you might expect. Simple stuff. Alrighty, that'll do us for today. I just wanted to touch base quickly. I'm getting around to doing a bunch of things, but always things, time is of the essence these days. Thanks for watching. I'll catch you later. Bye.